Okay, I thought I would show off my latest development of what started out a long time ago with the loss of my son, a pursuit of studying Nathan Stubblefield, and it went through all kinds of people. But one person that stuck with me was Eric Dollard. We might as well call him Sir Eric Dollard, because he came up with something called the analog computer in two different modes, at least, that I first learned about: the transverse mode and the longitudinal mode, which is a very long title. That's just the first word of the title, and so the short form for the longitudinal mode is LMD, which is short for longitudinal magneto-dielectric. We'll just say LMD. I was very impressed with that, and I thought, well, gee, I'm going to buy an electric car to make my show of support for free energy, because it's going to commit me to try to study free energy and come up with a solution to the very limited range on that car and all the trouble we have to go through to recharge it. And it was a big investment. I won't tell you how much, but it was a lot more than what it's worth resale value, I'll put it that way. But it has the distinction that the prior owner put it in a car show, and it has two of its pictures, two of the pictures of the RAV4 EV 2002 model is that car, my car, in the Wikipedia entry for the RAV4 when they talk about the electric version, the first generation. Anyway, my car is famous. So, I guess for good reason, because that was my commitment. I wasn't just buying something convenient, because if I wanted something convenient, I would have gotten a Leaf, although it wasn't very safe at the time. But I got that car because of the nickel metal hydride batteries. So it had a history of safeness, and of course I couldn't afford a Tesla. Anyway, not to get off topic too much. But I felt that somehow Eric Dollard's LMD modules could somehow turn the motor into a source of power. And I was getting ahead of myself, because I realize now that when you make a circuit a monopole, if we consider it separate from the load, then when we add in the load becomes one end of a dipole, the circuit becomes the other, and now we've got a dipole in which, when the demand goes up, made upon the circuit by the load, the power goes up, delivered by the circuit. And funnily enough, as Maharishi would say, funnily enough, that's the definition of a negative resistor, in which we get a certain proportion upside down. You know what? I think I should draw it so it looks very... I'm going to bring it up on the web. That's it. So I'm going to type in negative. Let's see, negative. Negative resistance. There we go. And we bring it up. Alright, negative resistance. We actually have well, now if my little camera can focus. Hello, focus. Come on now. What do I have to do? Jiggle the camera? Maybe I have to change the zoom in and zoom out. It doesn't want to focus, does it? There we go, finally. Now what you see over here, if I can find my finger, on the right hand side is the picture of a fluorescent tube. And sure enough, I'll read you what it says there in case you can't see it. Fluorescent lamp, a device with negative differential resistance. In operation, an increase in current through the fluorescent tube causes a drop in voltage across it. If the tube were connected directly to the power line, the falling tube voltage would cause more and more current to flow until it destroyed itself. To prevent this, fluorescent tubes are connected to the power line through a ballast. The ballast adds positive impedance, AC resistance, to the circuit to counteract the negative resistance of the tube, limiting the current. Now, over in this paragraph, in this column of paragraphs, let's see that they say the same thing. Let's just read from the beginning. In electronics, negative resistance is a property of some electrical circuits and devices, basically gas discharge tubes in the case that I'm, oh dear. So now reading from this column here. In electronics, negative resistance is a property of some electric circuits and devices in which an increase in voltage across the device's terminals results in a decrease in electric current through it. In other words, let's go down a bit. Where do they show that Ohm's law business? Oh, I think I missed it. Oh, here we go. Definitions, here we go. So this little relationship over here, I don't know if you can see it, since I'm already zoomed in. Static resistance, is that what I want? Well, you could see, then now they could have said the inverse. I don't know why they said that. Unbelievable. Turn things around so you don't get... That's weird. Where is the right one that showed... They keep putting voltage over current. Why on earth would they do that? To hide the fact... Explanation of power gain. Is this where I saw it? No. They're really trying to hide it. So they're not being totally upfront. I guess they're trying to do it the only way they know how. I haven't read through the whole article. Maybe that's half my problem. Alright, so they do something kind of quirky. Let's see, static conductance. Here we go, static resistance. In which they make resistance equal to voltage over current, or amperage. And that's not true to life. What you can do is swap resistance with amperage so that voltage divided by resistance equals amperage. And that's the correct way, well, for the purpose of my discussion, that's the correct way to look at it. It's the same equivalent terms. I don't think they want to explain it that way because then it starts looking ridiculous. It starts looking like Overunity. God forbid that should happen. I don't know what they mean by static resistance. Resistance is fixed as it is. So I guess I'm going to have to read this article to see why they make the distinction. If it's their complicated way to hide the truth, because the truth is very simple. If you're going along, voltage is ultimately what a battery contains. And it's what delivers. It also has amp hours, but that's something else. That's the capacity of the battery to deliver that voltage based on how quickly you deplete it. But if we forget about that, the amp hours of a battery, just think about the voltage difference between the two terminals. If we have that voltage, that's pressure. That's like walking along. You know, we apply a certain amount of pressure. Usually we think of it as force, but just think of it as pressure for the moment, because we have to push, you know? We got to push ourselves along, especially if we going uphill or in a headwind. Well, that uphill or a headwind is friction. That's resistance. And the greater is that resistance, the more we got to push. And so the push that we apply is pressure, and the resistance that we get competing against us, that's the resistance. Well, normally you would think, okay, if you want to go faster, you got to either apply more pressure or reduce your resistance. Better yet, walk downhill. And gravity will help you go faster, and you won't even have to apply pressure to go faster. You'll have to apply pressure to apply the brakes so you don't fall on your face. Well, walking along level ground is like zero resistance. Anyway, I guess it would be in both cases. When the resistance is greater, see, so that we're not even looking at the right. See, I'm going to have to draw it myself. All right, much better. See, they had the current swapped with the resistance. They had the resistance over here and the current over here, which is basically the same thing. 8 over, no, let's see. So if I keep coughing, I'm getting over a cold. Here we go. If we had the numbers 8 over 4, the answer would be 2. Well, if we swap the 2 and the 4, put the 4 over here and the 2 over here, 8 over 2 equals 4. So it still comes out to be a right answer. So we can swap these two numbers, and the equal sign still applies. So I just swapped them. And so now I have friction underneath pressure giving me speed, and that's positive resistance. So we're walking along applying a certain amount of pressure, and we reduce that pressure by the amount of friction that is being applied to us, and the end result would be how fast we end up going. That's normal resistance that we're familiar with, okay? Now we throw a little monkey wrench in here. And negative resistance, this relation up here becomes the reciprocal. In other words, 1 over. You know, if you take 8, 1 over 8 becomes 1/8. It becomes the reciprocal of 8. A fraction. Actually, 10 is a better example because the reciprocal of 10 is 10%. 1/10, 1 over 10. Well, here now, friction is divided by pressure. So, given a fixed amount of pressure that we apply walking along, now the more friction we have working against us, the faster we end up proceeding along. That makes no sense, yet that's exactly how a gas discharge tube operates, such as a fluorescent tube without a ballast or a neon bulb. A standard neon bulb comes without any sort of ballast. It comes with a resistor to protect it from surges blowing up or breaking the neon bulb. But they come pretty much as they are, and so as they come, they're already a negative resistor. And if we use them in a circuit, we have negative resistance in the circuit. So let's go find our little picture here. So here we have my little circuit that I've developed with multiple switches, and because I already have, well, I thought the best way to name it was to say a 3-lamp circuit, because it uses one LMD module of Eric Dollard. And an LMD module basically will have 2 coils, 2 inductors in other words, on opposite sides of a square relationship, and 2 capacitors on the other 2 opposing sides. And in this case, when power goes across this way, with the capacitors in the middle of that direction, this is LMD mode. If I was to proceed this way with my power, see my power over here on the left is hooked up to these 2 sides of the outside of the transformer. But if I had hooked up my power on the outside this way, my power source, to the 2 outside connections to the 2 transformers, then I'd be analoguing, I'd be bench testing a AC transmission line a normal AC transmission line in transverse mode, transverse electromagnetic mode, in which the capacitors represent the space between the wires and the coil represents the distance of the wire itself. But in LMD mode, you're doing the opposite. You're creating a transmission that's very unique. Well, it's different from the way we normally think, and it has some very interesting outcomes. So I have two spark gaps drawn across parallel to the outside of the LMD module. One up here, one down here, and I don't know if I need two. I just thought it looked aesthetically pretty. So I haven't tested that part out to see whether I really need two or not. But each one has its own capacitor, 47 nanoamp capacitor, to try to slow down or make the discharging of the spark gap, which is simulating a neon bulb, to make it happen periodically rather than constantly kind of thing. Make it go bunk, 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 nice little sharp pulses. Now I have 3 lamps for a reason. The point of this is to see how I can regulate Overunity, because in my very first Overunity simulation, it gradually increased very innocently, very slowly. I was like, oh, this is nothing, it looks boring. But once the voltage reached a certain level, because I think the LMD module serves as an oscillator, a retention of oscillating power that slowly accumulates. And once it reached the strike voltage of the neon bulb spark gap of 65 volts, it just took off. And when I cut the power, it took off even faster. In other words, it was putting out 150 billion gigawatts of power. 150 billion gigawatts of power when I destroyed it, because that was the only way to stop it from running. So I decided, okay, Overunity is easy, and then I learned since then that there might be another problem. There might be another problem, and that's when waves get out of phase, the voltage and the amperage and different things, and if the power source, where's my finger? When the power source starts registering high, like megawatts, it's being strained, and that's no good either. You don't want the power source to be strained. So I needed a means of regulating Overunity to make it reasonable. And so I started monkeying. I figured, okay, I'll just start with one LMD module, and I'll put in 2 flanking spark gaps with their adjacent capacitors, and see what else I can do. Well, let's see. Maybe I should... I had one outside lamp. Okay, that's the outside. It goes to where the spark gap is, because the spark gap goes to the outside connection point on the interior of the transformer. It's the same connection. So this first lamp is my outside lamp, but these 2 lamps are hooked up to the inside on either side of these 2 inner capacitors. They're the ones who store all the charge, tremendous amount of charge. It starts out like kilovolts. But I discovered, for symmetrical purposes, each of these 2 inner lamps that are actually positioned outside the circuit, but they're inner lamps because they're connected inside the LMD module itself, they need to be connected on a diagonal. So one lamp connects to the upper right, lower left, and the other is the upper left, lower right. Well, I discovered also that I can spike. I can send power. Normally the power gets sent to the outside of this leftmost transformer, just like this first lamp over here takes its power off of the outside of the rightmost transformer. So the outside coils on these 2 transformers is where the inner lamp, the outer lamp, this first lamp, the outer lamp, the power source, and the connection points for the 2 spark gaps and their associated capacitors, that's where they link up, on the outside of the LMD module. So I figured, okay, if I'm going to be draining the LMD module from the inside with these 2 additional inner lamps, why don't I spike it from the outside? So I have not only the power source going to the outside of this left side of this leftmost transformer, but I also have it go to the inside of the LMD module. And since I gave myself only one option of 2 leads coming from the source, I arbitrarily chose which diagonal to use to go inside. And then I made it on a switch, that toggle switch. It toggles between spiking versus drainage. And the only thing about drainage is I short out both sides of these inner capacitors because they really store charge. And to use, where's my finger? To use these lamps as the sole source of drainage takes forever. You'll be sitting there for hours, if not days. There's got to be a faster way to drain. Okay, the lamps are a minor way. It drains slowly with the help of these 3 lamps. But I needed a faster way. So as an alternative to spiking, there's shorting out the 2 sides of these capacitors. So you either short them out and drain very quickly, or you spike them with additional power. Or you turn off your power source and you spike them anyway, directly. So you got all these options. You got, let's see, where's my finger? You got the power switch, which is normal power down here, just on and off. Then you have your 2 spike switches that spike versus drainage, or spike versus, actually I should change that term. Spike versus, well, I say drain versus spike. I should say short. Well, it's the same as drainage. Yeah, I said drain because, drain ends up being the same thing. So my 2 drain versus spike switches work in tandem, or work in conjunction with each other simultaneously over here and here. Then I have a, where is it? Where did I put it? Oh yeah. Then I have the outer lamp switch for this first lamp, and it works all by itself. And then if I can bring in my 2 fingers, here we go. And then I have these 2 switches that are my 2 inner lamps, and they work together. They toggle on or off to engage these 2 lamps with the inside of the LMD or disengage them. And the only option is to engage, because the other end of my toggle switch in both cases leads to nowhere. Whereas here, at least you get something functional, depending on which way you throw the switch. And that's about it to describe. I found that when I shorted out the 2 sides of the capacitor, the voltage goes down, but for some reason the simulator shows current is still flowing. So I decided to put in a resistor here and here when I short out these 2 inner capacitors. And it can be a minimum of 1 ohm resistor. It didn't have to be 100. I just chose to make it 100. If it's 1 ohm, it'll stop the current immediately. If it's 100 ohms, it takes a little longer. But I thought 1 ohm was a little funny. A 1 ohm resistor? That doesn't look right. So I don't know. I make aesthetic decisions. It may not exactly be logically correct, because I'm telling you, it's not. 10 ohms would probably be a quicker drainage effect if you want fast drainage of these 2 inner capacitors. But maybe not. Maybe it's dangerous to drain them quickly. So maybe even a higher resistance of these 2 resistors would be more better. Maybe a kiloohm each, or a megaohm. What do I know, right? Or a gigaohm. What do I know? Now these 2 inner let's see, the 2 inner capacitors are 10 millifarads each. Now the capacitor up here that goes with its spark gap and the one down here that goes with its spark gap, they're both 47 nanofarads. The spark gap is configured for a neon bulb simulation. I got the information off the internet, so I didn't change that. Strike voltage of 65 volts. I'd have to read it off. I'd have to get you the let me get to that in a minute. Well, no, let me bring up the circuit. Let's see, where are we here? Alright, let's bring up the actual circuit and I can read off the values. Okay, it's in the lower right hand. Can I see it? Where are you? There it is. No, we can't see it. Okay. Alright, so that doesn't show all the values though. Oh, forget it. This isn't going to work. Wait a minute. Oh, this is all wrong. Okay, whatever. So this is the actual circuit, and if I bring up the edit window, see, there we go. If we can focus in on that without ODing on the illumination. you can see that the on resistance is 3 kiloohms, the off resistance is 10 megaohms, the breakdown voltage is 65, and the holding current is 3 milliamperes. So that's how I have, that was the parameters for a neon bulb to be simulated that somebody gave online, and I just went with blah, blah. I just went with that. I didn't try to change anything. But I found by trial and error a 47 nano farad capacitor to go alongside it helps to make those nice flashing neon bulb as opposed to a constantly on neon bulb. Now when we get inside, I said that the inner capacitor was 10 millifarads. Now the transformers are a pair. They exactly match. Now I've had a real tough time and I'm still not sure about this, so if anybody knows differently, please correct me, especially if you're Paul Falstad or Eon Sharp. In fact, I'm going to have to ask them. They have a very quirky... You can draw these transformers to flip around just by... When you draw them in, you can drag your cursor, hold it down and drag it to the right or drag it to the left. I noticed that with center tap transformers. You can literally orient a transformer any way you want. Well, I chose not to differentiate. I just drew them from left to right. That means my primary is on the left side and my secondary is on the right side, which is a little weird. And so the settings I have them for are peculiar, because if I bring up the edit window, the setting I have it, oh, I don't even have it right. That's supposed to be 100. Oh, shoot. Dang it. Oh, phooey. Yeah, I have to say phooey because... Oh, darn. Wait a minute. That's the wrong one. I'm going to have a problem. My link is not going to work anymore. My shortcut link. It's supposed to be 100 millihenries. I don't know why I didn't change that. Micro? Why did I make it micro? Oh my god. So this is a completely different setup than what I had originally experimented with a long time ago. Well. Save that. Export it. Alright. So, apparently, I'm going to have two different links. A 3-lamp LMD, which is, oh, you can't really see it. If I bring up the edit window, you can see it. There. So that's my link. But that gives transformers of the old way that were 100 microhenries each, and I don't want that. As I recall, 100 millihenries were the correct figure, but so I don't even know how this behaves. I haven't tried it with these values, because in my prior developmental experimentation, that's what I used, 100 millihenries. And anyway. I have a 50-to-1 relationship, which means the left side of each transformer is 50 times more inductance than the right side, because the circuit assumes I knew what I was doing when I drew them, and so I put the primary on the left and the secondary on the left. Well, I did the same thing with the left transformer. So I really have it weird, and yet when I monkeyed with it, that worked out the best. Wouldn't you know it? That's why I always draw them from left to right, because that's the way it works out the best. Now it's funny, in the right hand corner it says 1 to 50. I wonder why it says it that way, even though... Oh, it just assumes the primary is on the right side. Oh, when you draw these dragging left to right, they assume you're dragging from the direction of the secondary on the left-hand side and the primary on the right-hand side. That must be why they do that. I'm sorry, here I go again. So that tells me that the right-hand side is the primary of these transformers and the left-hand side is the secondary. So all my windings, my my windings that are 50 times more than the other side are on the right-hand side, on the right transformer as well as on the left one, which is really screwy. But hey, that's the way I found it works better. Okay, so if that's the case, the voltage comes in from the left under normal mode. If I'm not spiking this, I'm draining it, oddly enough, which doesn't make any sense. God, that doesn't make any sense. I need another switch in here. I need another switch right in here. You know what? That's what I'm going to have to do. I'm going to have to put in a third switch, which will be a third option. Actually, I needed a three-way toggle switch is what I needed. But I could just as easily put a one-way switch over on this leg, and I don't know where I'd put it here. It's such a clutter. Oh, I'd put it right here. I could put a one-way switch right there. Okay, so I got some more development to do. That way I just realized I'm draining these at the same time that I want to power it from the left side. Okay. So when I connect the power from the left-hand side here, let's see, if 50 times is on the right-hand side, that means, what does it mean? It's a step-up transformer. So I'm stepping up voltage from left to right and from left to right again. Which means this bulb over here is getting the benefit of two step-ups, you would think. I guess that's what I was veering for, was stepping up the voltage more than anything else. So this is not at all like Barbosa and Lille, because I would have had to turn one of these around, probably this one, because this has all the windings on the right-hand side which don't belong there. So I would have it be flipped over, and everything else would be the same. Yeah, I don't need to swap polarity because it's already connected top to top, bottom to bottom. So I would just have to take this transformer out and redraw it, drag it from left to right. I'm going to have to try that. Actually, the way I got around with doing this so as not to have to do that, instead of putting in 50 as my ratio, I would put in the reciprocal of 50, which is 2%. And so I've tried all those. I've tried 2%, and I've tried 50, and I've tried, there's 4 combinations possible, and this was the way that worked the best way, having the source of power on the left and the load on the right. So I figured, okay, whatever. I'm just monkeying it. I'm not trying to use logic. I just try to use trial and error at this point. At that point, I was using trial and error. So the only other thing I have to do is put in one additional switch, and then this 3-lamp LMD link is not going to work anymore, because it works for the other version of the 100 microhenry transformer version. It should be interesting at 3 millihenry. It should be a little different. But so you try different combinations of switches. So let's see. There's a power switch. There's the spike drain switch over here. There's the various lamp switches. You try different combinations, and you try them in different sequencing, because that makes a difference too, to see what kind of results you get. But one thing's for certain: you can drain this thing down. You can drain this inner LMD module down to 0 pretty quickly if you want to, and that was my intention. I never wanted to have to deal with retention of power in these two capacitors in the middle, these two 10 millifarad capacitors. I didn't want to have to deal with that, I should be able to drain it almost instantaneously, because this is where all the power gets stored. But I also want to be able to see a rise of power, but not a rise that goes to infinity. I've already done an example there. I think it's called the isgood, what's it called, shortcut URL, is.gd/extreme and extreme numeral 2, extreme 2. Those were my two. Then I have two others. I have wipeout, but that just shows what was left over. But I have extreme and extreme 2, I believe. Yeah, those are files. Those are text files, and you have to load them in. So, see, with anything else, I should have put in another link here. Sorry. That was another piece of information I left out. Blank canvas. That brings up a blank canvas. Let's, shall I do it? Let's see. Yeah, I already saved that part, so let's see. Blank canvas, where is it? I have a shortcut for that. So you get a blank canvas, and then you load in a file. So you import a local file. You will have already saved it because I'm giving you the link where to download them. And you load in, and there it is, ready to go. The switches are all in the position I left them in that I stored in memory. And I couldn't put any labels on these different scope outputs because that really screws up how this is centered and sized by the simulator. So I might as well go through that. The leftmost is obviously the power source, so it's operating as we speak, but just the voltage. The amperage is flatlined at the moment because the hot lead from this power source is not connected to anything. But the neutral I keep connected. Sort of. Actually, it's connected. Okay. The next one, you highlight it with your cursor and you find out what on the circuit board gets highlighted. Ooh, it's the spark gap up here. So you move your cursor over to the next scope and find out, oh, look at that. The spark gap, the neon bulb down here is highlighted. So that's the third scope value, is the bottom spark gap. And now we're doing the capacitors, the inner capacitors. So the topmost capacitor is the fourth scope value. The fifth scope value is the bottom inner capacitor. And then we have our three lamps. The outer lamp, which is lamp number 1. And then the two inner lamps. Lamp number 2, this one here. And then the last scope value is lamp number 3, which is also an inner lamp. But they switch again in conjunction with each other. So I have to add a switch, and I have to add another link, blank canvas, and I have to change this link to accommodate this new circuit. And then you just run it. You go get the blank canvas, you load, you go store the file on your computer. It's a text file. Now, if you want to monkey and edit it, I suggest you use a binary text editor, because that's the only way to, even though it's saved as a text file, you cannot monkey with the contents of the file with a normal notepad, kind of text editor, because that'll screw it up by putting in the wrong carriage returns. You have to use a binary text editor to do that, and I got mine from EditPad Pro 7. I paid a little money and it was well worth it. Then you can come in here and change the values. You'll learn eventually which ones have to do with the stored energy in various components. Like if there's a capital, this line up here, it starts off with a capital T, and that's a transformer. And these two lines below it is a lowercase c, and those are capacitors. So there are different ways that it signifies, and then I just zero out, when something's, eventually you learn. You put one circuit on a blank canvas, you store it as an exported file, and then you open it up in your binary text editor and look at it. And what does a normal component look like before it's engaged in a circuit and gets all powered up and starts to store energy? And that's what you look for as your norm of zero power or zero energy, whatever the values represent, I don't know. Zero energy, whatever, stored in that component. And you'll get energy stored in a transformer, in a capacitor. In the light bulb, you'll get temperature stored, at the very least, although I think you might be able to store something else as well. So there are different things, because the light bulbs are interesting. They'll tell you what temperature they're at in degrees Kelvin, and you can find out how hot they're getting. They're only about 180 ohms of resistance each, but they're nice. They light up. They tell you they need a certain amount, I think it's 1800 degrees Kelvin, in order to be bright white. So they go through different stages of color. It might be brown, and it goes to orange and yellow, and then finally when it gets to white, that's full operating temperature. Anything beyond that, the bulb probably exploded after a certain point. And so that's one thing about this circuit. It's totally unrealistic. It'll give values that a normal circuit would have fried itself, okay? But at least it's not going to infinity. So in order to make this practical, it takes a lot more tweaking to make it realistic. For instance, each of these lamps could be some kind of regulator, maybe a variac or a potentiometer or both, to try to bring down the values so you can regulate the power output. And then you would need sensors to sense the load so that, I don't know. This is just proof of concept that we can at least regulate Overunity and not so that it doesn't go to infinity. But whether or not it's practical is a whole other issue, and that I did not try to resolve in this circuit. I just tried to come up with a circuit that is doable, is simple enough, it's not too complicated, it doesn't have too many wires, too many switches, too many choices to have to make, to do what I want it to do. I want it to drain, I want to be able to spike the inside of the LMD module, as well as power it from the outside, as well as drain it from the outside. And that was pretty much it. And so I come up with consistent values. When you choose your various switch options, it'll take a while to get to its target value, the voltages and whatnot, and it'll stay there. And the other thing I didn't point out is each of these scope values, I've preset them to display 3 different pieces of information digitally. So it doesn't just put out the waveform. It'll tell you the high voltage, the low voltage, and the frequency. Because I was kind of curious whether or not I could find out, because I found in my experience that a lot of these waves tend to be like a harmonic, like 8 times longer than a normal 60-cycle sine wave. Problem is this simulator is not telling me that that's happening. I can see it. The wave on the scope shows it. You can stack. You can go up here. Let's see, where are we? You can come up here to, you can't really see it. You have different options, scopes, and you can stack the scopes, you can unstack them, you can combine them. So if you stack them, then all these scopes get stacked on top of each other, and then you can really see that some of the waves are really long, and you can count the number of wavelengths extra that they've become lengthened. It's pretty cool. So this software is pretty cool. It's not a bad piece of software. And again, the only reason why I went to this software is because I could not simulate a Kaptor loop, or a coil of wire, I should say, a coil of wire around another piece of wire, which is a crucial piece of component in Barbosa and Leal. So I had to give up Barbosa and Leal. And since I had already added Eric Dollard's LMD module, 3 of them, daisy-chained, as a substitute for the earth grounding rods, all I had to do was retain the spark gap, the neon bulb, and throw away everything else, because it wasn't contributing to the circuit because I didn't have it properly connected. And it's been a very interesting investigation and study ever since, because Eric Dollard's LMD module is similar to Barbosa and Leal's electric keeper, or Kaptor loop. Apparently, I've been misusing the term Kaptor loop. That continuous loop of wire that's 4 gauge, 4 Aug gauge, in the center of the 2 transformers of Clarence's replication. Those 2 transformers faced off like that is very similar to Eric Dollard's singular module, but with the lack of the 2 capacitors in the center. In the center, the 2 transformers. And by putting those capacitors in, okay, not too much of a difference, but it's the same concept because we've got 2 transformers faced off. And I still got the spark gaps. In this case, 2 of them, because I don't know if 2 is better than 1. I just thought, oh, well, aesthetically it looks prettier this way. Because I'm trying to balance top to bottom. Everything I do linearly across, or horizontally, is distinctive, except for diagonal connections on the inside, of course, of the LMD module. So sometimes I had to be aesthetic, and other times I was not. I was linear, because the only option, see, is to put the power and the load on the same side of the LMD module, and then just close off one end of the LMD module, the opposite end that you're not using. And that's where your power goes to infinity, your watts. So I realized I had to do something differently, so I put the power on one side and the load on the other, and then it becomes a regulatable situation. It becomes very controllable, very reasonable. So it looks like Overunity, okay, but still, I don't know. Maybe the waveforms are all wrong, and so, maybe I'm doing something wrong, and so it's wasted power, It may be Overunity, but it's all going to waste. I don't know. That's a very crucial question to be able to answer, and I don't know how to answer it, so I don't know if this circuit qualifies as anything other than a novelty. It may not be useful, even if it were put into practical terms. But I committed myself to come up with this, and so I came up with it, and it looks pretty good, but I'll just have to study it some more to find out if it's actually practical. Okay, I made the changes that I said I was going to make. I put in this neither switch. I call it a neither switch. So it's drain versus spike versus neither. If you can see that. Drain versus spike versus neither. And the way it works is this switch here and this switch down here, they're paired off together, they work as a pair, and all they do is they choose between drainage and spike. That's all they get to choose. You don't get a third choice. Now, if I had put a three-way switch in there, it unfortunately rotates through left to right or something, and that means you would have no choice as to which of your other two options you wish to go to. You have to go in a rotating motion, which means at some point you'll be spiking whether or not you want to. Now, I didn't want that. So a separate switch is necessary, and that's your neither switch. So that breaks the whole loop. And there's one up here, and it's paired with one over here. And they work together. And they're called my neither switch, because they break this little loop, this short between the two sides of the capacitor. Which in one mode, this switch over here shorts the two sides of the capacitor, but in the other mode, it spikes the inside of the LMD module, okay, on a diagonal. So that was my minor modification, and the other thing I had to do then was save a new text file and make a new shortcut link to it. And so the shortcut link is 3lamp _ uppercase LMD and the number 3, and that's the online location of the text file that you load into blank canvas. So you use the shortcut link of blank canvas, and I misspell canvas with a double S, and there's no space there between the two S's. That's just a mistake of the simulator that it makes it look that way. So you load a blank canvas by using the misspelling of the word canvas with a double S, all one word, no underscore, and then you go and save the text file 3lamp _ uppercase LMD numeral 3, and then load that into your simulator using your file. This is all in JavaScript. This is pretty cool. Using your file, and you'll have an option import from file, because I exported it to file because there's too much information in this circuit to save it as an exported link. That would have been nice, But this way it's a 2-link process rather than a 1-link process, because there's just too many components to save. I mean, the link would have gotten to be over 200 characters long, and browsers don't like that. So this is why I had to do it this way. Hey, whatever works, right? So this is my little circuit, and play around with it and see whether or not you like it, or make comments, whatever. Or don't. Ignore me. No one wants to. Okay, enough already. I'm just putting it out there, for better or worse, or for nothing. All a waste of time. No, it wasn't. It was fun. I'll have to play with it myself. I've only played with it enough to know how to put it together. But I need to play with it some more, obviously, so whatever. Well, I went back to this particular circuit as my reference because I wasn't sure about the transformers in the middle. Are they 100 millihenries or microhenries? Which were they? And so I went back to it and I find out they're microhenries. Oh my God. I thought that was too dingy. The capacitors on the inside are 10 millifarad capacitors, but the henries on the transformers are 100 microhenries. So I went back to here as my reference, and then I went and changed it in here. So I had to make a whole new shortcut link. So now it's 3lamp underscore uppercase LMD numeral 4. And so between 3 and 4 you can monkey with it and see what kind of results you get. 100 millihenries for the LMD3 versus 100 microhenries for the LMD4 version. So different versions, play around with it and see how you like it.